A-level mechanics, Newton's third law as applied to pulleys. Newton's third law says that when two bodies interact, the force on one is equal and opposite to the force on the other. We're going to see how this applies to bodies connected by strings passing over pulleys. Now the diagram shows two particles connected by a light string passing over a pulley. In the diagram, we can draw in the forces acting on each body. Well, first of all, we've got gravity, and in each case, the force of gravity is equal to the mass of the body times g, which is 9.8. Now, if there's no friction between the pulley and the string, we say the pulley is smooth, and the tension will be the same along the length of the string. This means the tension on each particle will be equal. We can call the tension T. Now, if the string is inextensible, then both particles will have the same acceleration, one down and one up. If one moves down, then the other will move up by exactly the same amount. And at any given instant, they will both have equal speeds. To analyse the situation, we must consider the forces on each particle individually and apply Newton's law F equals ma in each case separately. Let's have a look at an example, example 1. Particles A and B of mass 3 kg and 4 kg are attached to the ends of a light inextensible string. The string hangs over a smooth pulley. When released, find the acceleration of each particle and the tension in the string. Well, to solve this, on the diagram mark in the forces. On particle A, we'll have gravity acting downwards. Now the mass is 3 kilograms, so the force of gravity is 3g newtons, where g is 9.8. And acting up, we have the tension in the string. We can call that T. Now we'll assume the particle A, being the lighter particle, moves up. So we'll give it an acceleration in the upwards direction of small a. If we now look at particle B, this has a force of 4g acting down because of gravity. Also, because the string is light and the pulley is smooth, the tension is the same all the way along the string, and so the tension pulling particle B up will be T, the same as on tension A. Finally, because the string is inextensible, the acceleration of B will be the same as the acceleration of A, but going down. Now we can use F equals ma on each particle individually. Resolving vertically upwards on A, we get T minus 3g equals 3a. We can call that equation 1. And then resolving vertically down on particle B, we get 4g minus t equals 4a. And we can call that equation 2. Adding 1 and 2, we get g equals 7a. In other words, a is equal to g divided by 7, but g is 9.8. So a is 9.8 divided by 7, which is 1.4. And so the acceleration is 1.4 meters per second squared. Now if we substitute that in equation 1, we get t minus 3g equals 3 times 1.4. So t is 3 times 9.8 plus 3 times 1.4, which works out to be 33.6 newtons. So we have an acceleration of 1.4 meters per second squared with a tension of 33.6 newtons. Let's look at example 2. In the diagram, there are 3 particles A, B and C of mass 2 kg, 4 kg and 1 kg connected by 2 light inextensible strings. They're held on a smooth table with C hanging over the edge from a smooth pulley. In part A, we want to find the acceleration of each particle. Well, we can start by drawing a diagram and marking in the forces. Let the tension in the first string be S. And let the tension in the second string be T. Because the pulley is smooth and the string is light, the tension will be the same at both ends. Particle A will have a weight of 2g, which is 2 times 9.8, and a normal reaction we can call m. Particle B will have a weight of 4g, or 4 times 9.8, and a normal reaction we can call p. Particle C will also have a weight of 1g, or 9.8. Because the string is inextensible, all three particles will have the same acceleration. We can call that A. Let's consider each particle individually. Now, if we resolve horizontally on A using F equals ma, we have S equals 2a. We can then resolve horizontally on B using F equals ma, and this gives us T minus S equals 4a. And resolving vertically on C using F equals ma, we have 1g minus T equals 1a. So if we add equations 1, 2 and 3, we get S plus T minus S plus 1g minus T equals 2a plus 4a plus 1a. And that simplifies to 1g equals 7a, or a is equal to g over 7, which is 9.8 over 7, which is 1.4. So the acceleration is 1.4 meters per second squared. And for part B, we're asked to find the tension in each string. Now we have S is equal to 2a, which means S is equal to 2 times 1.4, and so S is equal to 2.8 newtons. T minus S is equal to 4a, so T is equal to 2a plus 4a, which means T is 6a, or 6 times 1.4, which is 8.4. So we get the tension S is 2.8 newtons, and the tension T is 8.4 newtons. Example 3. Two objects, A and B, are connected by a light, inextensible string which passes over a smooth pulley. Object A has mass 8 kilograms and rests on a plane with slope of 30 degrees with the horizontal. There is a frictional resistance of 4.9 newtons between the object and the slope. Object B has mass 6 kilograms and is freely suspended, as in the diagram. When released, in part A we're asked, find the acceleration of the two objects. To solve this, first we need to decide which way the two objects are going to move. Although the 8 kilogram weight is the heavier weight, it's on a slope, so it's likely to move up. Now we can draw in the forces. So the forces acting on A are its weight, which is 8g, where g is 9.8. We have a normal reaction, which is at right angles to the plane. We can call that N. We have the tension in the string, which we'll call T. And we have the frictional force. Now, because we're assuming it's moving up the plane, the frictional force will be down the plane, 4.9 newtons. If we look at particle B, it has a weight of 6g, or 6 times 9.8, and there's a tension in the string. Because the pulley is smooth, this tension is T. It is the same as the tension on particle A. Finally, because the string is inelastic, both particles have the same acceleration, one up the slope and one vertically down. We also notice that the weight of object A makes an angle of 60 degrees with the slope. Let's consider particle A on its own. Well, we can resolve up the slope using F equals ma. Note, when we resolve the weight of the object down the slope, it's the weight of the object times the cosine of the angle between the direction of the weight and the direction of the slope. This is 60 degrees. So we have t minus 8g cosine 60 minus 4.9 equals 8a. And that evaluates as t minus 39.2 minus 4.9 equals 8a, or we can simplify it, t equals 8a plus 44.1. We can call that equation 1. Now, if we look at particle B on its own, we can resolve vertically down, and we get 6g minus t equals 6a, which we can rearrange as t equals 58.8 minus 6a. We can call that equation 2. We can eliminate t from equations 1 and 2 to get 8a plus 44.1 equals 58.8 minus 6a. And that simplifies to 14a equals 14.7. So if we divide both sides by 14, we get a is equal to 14.7 over 14, which is 1.05. So we get an answer. The acceleration is 1.05 meters per second squared. Now in part B, we're asked to find the tension in the string. We have T is equal to 8a plus 44.1, and we know A is equal to 1.05. So that gives us T equals 8 times 1.05 plus 44.1, which means T is 52.5. So our answer is the tension is 52.5 newtons. Now in part C, we're asked, find out how long it would take A to travel 8.4 meters. Well, we have the distance S is equal to 8.4, A is 1.05, and the initial speed U is 0. We're trying to find out the value of T. So we can use the Suvet equation, S equals ut plus a half at squared, to get 8.4 equals 0 plus 0.5 times 1.05 times t squared. And that gives us t squared is 8.4 over 0.5 times 1.05, which works out to be 16. So t is the square root of 16, which is 4, and so the time is 4 seconds. Example 4. A light inextensible string is attached to the ceiling and then passes under and over 2 light smooth pulleys, as in the diagram. The first pulley is free to move and supports a mass A of 6 kilograms attached by a short string. The second pulley is fixed to the ceiling. There is a mass B of 5 kilograms attached to the other end of the long string. When released, find the acceleration of each mass and the tension in each string. Well, to solve this, we first need to find out how the pulleys and weights move relative to each other. If we look at the diagram opposite, we see that if the 6 kilogram weight moves up a distance x, the string above it will shorten by a length of 2x, which means that B will drop down a distance of 2x. So we see when A moves, B moves twice as far, which means at any given point B will have twice the speed of A, and it'll have twice the acceleration of A. If A has an acceleration of A up, then B will have an acceleration of 2A down. Now show the weights of A, which is 6g, and B, which is 5g. Let the tension in the short string be S, and in the long string be T. Let's first consider mass A. If we resolve vertically using F equals ma, we get S minus 6g equals 6a. But 6g is 6 times 9.8, which is 58.8. So we get S equals 6a plus 58.8. Call that equation 1. Now if we look at particle B and resolve vertically using F equals ma, we get 5g minus t equals 5 times 2a. But 5g is 5 times 9.8, which is 49. So we have t equals 49 minus 10a. And that's our equation 2. Then if we look at the moving pulley, resolving vertically using F equals ma, we get 2t minus s equals 0a. The pulley is light, so we take the mass as being 0. That means s equals 2t. That can be our equation 3. If we substitute equations 1 and 2 in 3, we get 6a plus 58.8 equals 2 into 49 minus 10a. And if we expand the bracket, that's 6a plus 58.8 equals 98 minus 20a, or 26a equals 39.2, and so a is equal to 1.5077. So we have the acceleration of a is 1.51 meters per second squared, and the acceleration of b is twice that, 3.02 meters per second squared. Now to calculate the tension S, we have S equals 6a plus 58.8, which is 6 times 1.5077 plus 58.8, which turns out to be 67.8462. And we have T is 49 minus 10a, which is equal to 49 minus 10 times 1.5077, which equals 33.923 newtons. So we have the tension A is 67.8 newtons, and tension B is 33.9 newtons.